Morning. Hope everybody's doing well today. Um, I'm going to be starting our first optional video on the remaining content in Calc BC that's not going to be on the exam, but something I think is still important for us to know, for those that would like to know. We've learned about some integral tests, or I'm sorry, we've learned about some tests already for convergence and divergence. Okay, the two main ones that we need to know for the AP exam were the alternating series test and the ratio test. Okay, we learned those the last 2 days. I'm going to kind of jump backwards a little bit, go to the first day of this unit that was optional now, but we're going to talk about the integral test. The integral test and its error bound as well. So originally I had a warm-up that was going to be practicing some old stuff, and this was improper integrals. Okay. I'm not, for the sake of time and just for video purposes, I'm not going to go through these slides for you, but just to kind of refresh you on what they are doing. Like for instance, remember improper means that the bounds are not defined or go to infinity. So like for instance, this one is negative infinity to 0 in number one. So you would set this up as the limit, and we use the letter r as a replacement for our bounds. We would say r is approaching negative infinity in this case, because that's the one bound that's not defined. And we would say r to 0 of x squared e to the negative x cubed dx. Okay, and then we go through the motions and solve that and so forth. And in our problems today, we're going to have to be doing that, so we'll just kind of practice it there. But most of these are completed online if you want to try those out. But I'm going to go ahead and jump into today's notes. All right. Let's see here. Sorry, I'm trying to get rid of this taskbar. Nope. Maybe some way to do that, right? Oh well. Okay. So in this section, um, we will, and then the next three sections, which actually we've already covered two of those, they're going to provide tests to determine whether a series converges without explicitly finding the sum. So we've already learned two of them. The two we've learned was the alternating series test, and we learned the ratio test. We also know the root test. Okay, we know the test for divergence, and that's about it. Okay, so just as a reminder, so usually to this point we would have only known one test, and that was coming from this theorem here. If a series from 1 to infinity of a sub n is convergent, then the limit of a sub n equals 0. Remember, we get the test for divergence. All right, the test for divergence from that logic. And that's what the next slide is saying as well. So remember that the test for divergence, okay, simply says that if the limit of a sub n does not exist or does not equal 0, then a sub n diverges. And like I said, prior to all of our tests, that was always our first one to go for because it's the easiest. And today's lesson was the only one we really knew going into this lesson. Okay, so that was the only one that we needed to keep in mind. Okay, but now we're going to add to that. We're going to add the integral test. So here's where the lesson really begins on the integral test. So for every single one of these methods, I told you you gotta identify certain types of functions that to do certain tests for. And I think, me personally, I think this is the hardest one to be able to identify when to use it, because you use it whenever it's easy to integrate. Whenever you have a series that you can easily integrate, because the test itself is not bad at all. So it says, suppose f is continuous, positive, and decreasing function for all values of n from 1 to infinity. And we're going to let a sub n equals f sub n, meaning we can make a function instead of a sequence, because we want to integrate the function, not the sequence. Then, case number one, if the integral from 1 to infinity of the function f of x is convergent, then the summation of a sub n is convergent. And if the integral 1 to infinity of f of x is divergent, then the series is divergent. So basically what I'm saying is if f is convergent, then the summation of a sub n is convergent. And same with divergent. So if I can take, and f is just no more than a sub n as a function. Okay, that's all that is. Now I like this next part right here, and I think this is very important to note here. It says, when using the integral test, it is not necessary to start the series at the integral n equals 1. And here's the big one here. It's not necessary that f is always decreasing. That's one of the criteria above, but we talked about this term before. It's just the fact that it's ultimately decreasing. You're going to see that is a little stretched in some of the examples, but ultimately that it's decreasing. Okay. So let's jump into actually doing some examples. All right. So first example, we're going to test the series for n equals 1 to infinity of 1 over n for convergence or divergence. Now, we have already had many talking points on this series 1 to n, or 1 over n. We know by now that this is a harmonic series, p series where p equals 1, and we know that that means that it's divergent. Okay, we know that this is divergence from many discussions before this. Okay. But we are going to we're going to show that. Okay, we are going to show how that works. So using our integral test. Okay, so pretty simple. We are going to pretty much take a sub n and turn it into a function. So we're going to say, instead of a sub n, we're going to say f of x equals 1 over x. Okay, that's the function that we're talking about. And there is some criteria. This is the only annoying part with integral test in my eyes. There is some criteria for using it. Is that we do have to show that it's positive, decreasing, and continuous. Okay, we have to show those three criteria from before. All right, we have to show continuous, positive, and decreasing. So I usually do it in this order here. I'm going to talk about it being continuous. I'm going to talk about it being ultimately we can say decreasing, but we'll say positive first, and then lastly, there's decreasing. Okay. And a lot of these are pretty logical. Like continuous, it's a rational function, so it's continuous from negative infinity to 0 and 0 to infinity, and that's talking about x. Okay, so, and if that's the case, then the sequence would also be continuous on that same interval. So I'll say thus or therefore n is continuous, and the interval that I care about for n is from 1 to infinity, and that's a part of my continuous interval. So I know that n is continuous from 1 to infinity. Okay, so that's good there. When is this function positive? Well, we probably know that it's positive from 0 to infinity. And therefore n is also positive on that same interval, but more specifically 1 to infinity, because that's where my sequence is starting. And decreasing, again, remember how we show decreasing is based off of the derivative. So it's like f prime of x equals negative 1 over x squared. And no matter what term I plug into that, it's going to be negative. So it's decreasing from negative infinity to positive infinity, And in terms of n, it would also be decreasing on that interval because that's included in the interval for x. So we just showed that for the n values from 1 to infinity, that is always continuous, it's always positive, and it's always decreasing. Okay. So if that's the case, then I can do the integral test. Now the integral test simply says if I were to take the integral from 1 to infinity, all right, of my function that I have defined, which is 1 over x, okay, if that is convergent, meaning if that equals a number, then my series is also convergent. If that equals anything other than a number, like infinity or does not exist or something, then my series is also divergent. Okay. So we're going to go through the motions, and this is an improper integral. That's why I had that warm up before. But now all I'm going to do is I'm going to say the limit. Okay. The limit. Do this. As r is approaching infinity. Okay. Of now instead of the integral 1 to infinity, it's 1 to r of 1 over r. Sorry, 1 over x. I apologize. Haven't integrated it yet. Dx. Okay. So all I've done is just go through the motions of improper integration. So now remember what we do is we'll do the limit at the very end. We're going to do limit as r is approaching infinity. And I'm going to go ahead and integrate it. So that's going to be ln of absolute value of x, okay, evaluated from 1 to r. I'm going to plug in r, I'm going to plug in 1, and I'm going to take the limits. So I'm going to say the limit r is approaching infinity, okay, of the ln of absolute value of r minus the limit r approaches infinity of the ln absolute value of 1. Okay. So if I take the let's start with piece by piece. If I'm doing the limit, if I'm doing this part right here, the limit is r approaches infinity. Now, if I keep plugging in higher and higher numbers into that, that's just going to end up being infinite. This limit is equal to infinity. So that's going to be infinity minus, and then the ln of 1 is just 0. But remember what we said, any piece of it is undefined or infinite, then we would say divergent. Now, for sake of time, I'm only going to kind of write this out once, and then I'll let you kind of write it out from here. But I'm going to show you kind of how you would summarize this. You would say, since f of x is continuous, positive, and decreasing. Okay, we showed those three things. And divergent. So we showed all that about the function f of x. If that's the case, then the series that we represented as f of x, then the summation of n equals 1 to infinity of 1 over n also diverges. Because we let f of x be 1 over n, so if we showed the function was all that, but I should probably clarify, by, I'm going to say IT for integral test. And I see that I just covered that up with my video, so sorry about that. Let me, dadgummit, let me see if I can do this real fast. I'm going to go to select objects. Whoa. Can y'all see that there? Boom. So I should read that for a second. You can pause the video. I'll move it back down to where it was at. Okay. All right. Let's try another one. Okay, so um, again, this is the part that annoys me about all this is like, okay, like you do integral tests whenever the sequence is easy to integrate, like n over n squared plus 1 squared. Oh, that's easy to integrate. Well, how can you know that? I mean, that's kind of the annoying part. You can let the quantity inside here be u. So whenever you're doing integration, you could do u sub. So it's hard. Sometimes it's hard to see. Sometimes it's easy to see. I don't know. Okay. But in this case, we are able to do the integral test because I can easily integrate this. And I'm sure there's other tests that could also work for this, but we're going to choose to do integral test. Okay. So if that's the case, then I'm going to let f of x be equal to x over x squared plus 1 squared. Okay. And all right, so I'm going to show all those criteria again. I'm going to show that number one, it's continuous. Number two, that it is positive. And number three, that it is decreasing. Okay. If I can show those three things, then I'm allowed to do the integral test. This is a rational, and so it's continuous for every value except for what makes the bottom 0, and the bottom can never be 0 because it's x squared on the bottom there. So there's no way to get that to 0. So we'll say negative infinity to positive infinity for x, and therefore for n, it would be continuous from 1 to infinity. So there we go. Okay. Now, where is it positive? It's positive, so the denominator will always be positive because again it's x squared. So that means for the top, what makes it negative is whenever you go, well, for positive is when you go 0 to infinity. That's what makes the top positive and the f of x positive. That's for x, and therefore for n, it would be, and I should do that right there, and it will be positive from 1 to infinity. Okay. And then decreasing comes from finding f prime of x, and for sake of space and time, I'll let you find the derivative on your own. Well, I'll let you do the work to find the derivative on your own. I got down the derivative to being 1 minus 3x squared over x squared plus 1 cubed. That's what I got it down to it, and that's, you can check my math on that, but I did low D high minus high D low, and I got it simplified to that, but I'm pretty sure my math's right on that. Okay. So, and if you solve for where this is equal to 0, like the bottom doesn't equal 0, but the top does, x equals the plus or minus the square root of 1/3. And I tested that on my number line. So I put like negative square root of 1/3, and I put positive square root of 1/3. And if I tested some points in the derivative on my interval here, it went negative, positive, negative. So ultimately, it is decreasing. Like positive square root of 1/3, that's just like point something. Okay, so like 1 is right here. Okay. So that means that yes, for x, it's decreasing from positive square root of 1/3 on, but for n, it would be decreasing from 1 to infinity, because again, 1's like right here, and any point on from that is going to be decreasing. So, yay, we showed the three criteria. Okay, now what the integral test says to do is we're going to integrate this. We're going to show that 1 to infinity. Okay, we're going to show that the integral converges as it goes to infinity. So therefore, the sequence would also, or the series would also converge. Okay. So I'm going to go through the motions again. Do some work here. That's x over x squared plus 1 squared dx. I'm going to do the limits. See if I can get this right. The limit as r is approaching infinity of the integral 1 to r of x over x squared plus 1 squared dx. I know I'm getting a little ugly there with my handwriting, so bear with me. Okay. I'm trying to think about how much work I can show y'all with this. All right. Yeah, okay, I'll go through the whole thing. So like to integrate this, you let u be x squared plus 1, so du is 2x dx. So if I integrate this, that's going to be the limit r approaches infinity. Now we're going to go ahead, well, I'll just go ahead and replace everything. So I'm going to bring the 1/2 out, integration 1 to r of, instead of, well, the x dx cancels out. So that's just going to be the integral of 1 over u squared, or u to the -2nd du. Okay, and again, you know how to integrate. I can let you do all this math on your own. I'm just kind of going through the integral test real fast. But anyway, if we integrate that, that'll be -1 over u. Okay, so -1 over u, which I'll go ahead and substitute everything back in. That's the limit as r is approaching infinity. Okay, and if I integrate this, okay, so it's going to be negative, so we've already got the 1/2 there, so it's going to be -1 over u times 1/2, so I'm going to have 2 down here for the 1/2, and u is just equal to x squared plus 1, okay, and you could have done u bounds there. I kind of realized I didn't do that, but I could have, from 1 to r, okay. I'm going to plug r in and plug 1 in, and then we're going to see kind of what we get down to, okay. So I'm going to go over here and say that this is the limit r approaches infinity of the quantity -1 over 2 times r squared plus 1, okay, and then minus the limit r approaches infinity of the quantity -1 over 2 times 1 squared plus 1. Okay. Now, if you take each of these limits, okay, so like as r approaches infinity for this first one here, the r power on bottom is higher than on top. It's a rational. You can think of it as the bottom is going to infinity, therefore the fraction is going to 0. We've done that plenty of times. And then minus, if you simplify that down, it goes to -1/4, which equals a fourth. So because the area converges, because that means it converges to a sum, therefore the series converges. Ta-da! And I would prefer you to write it the way I did last slide, but I'm just not doing it for the sake of room and time. But there you have it. And now just to let you know, this 1/4 means absolutely nothing as far as like what the sum of the series is. That just is telling me that the sum does converge. It doesn't converge to 1/4. It might be close to 1/4, but it's not going to be 1/4. Okay, and I'll show that more so when we get to error bounds with this. All right, good on that. Let's try another one. Here's another one I like, and I think the dead giveaway for this one. This is one time I can kind of tell a giveaway is ln of n. If you see that, usually you do integral tests with that. Okay, so I'm going to go through the motions. I'm going to do f of x equals ln of x over x. So I'm looking at a continuous function here. Well, let's show that. We got to show that it's continuous. Talk about continuous, positive, and decreasing. Okay. It's continuous for every value that's defined, so that's everywhere but 0 in this case. So it's well, actually, and for ln you can't plug in any negative numbers into ln, so it's only continuous. It's only continuous from 0 to infinity, which in terms of n includes 1 to infinity. So we've showed that. We're good to go. Okay. Where is it positive? So let's see. It's positive on the denominator for 0 to infinity, and it's positive on the top from 1 to infinity. Okay, because if I plug in any like number between 0 and 1 on top, it's going to be negative, and then from 1 to infinity, it's going to be positive. So it's positive from 1 to infinity. And 1 is not included in that interval because 1 is where it changes from negative to positive. So we don't include that interval. So since we don't include 1, 1's not going to be included for n. The next number we would start with is 2. Or you could have just said 1 to infinity again, but because we're only using integers and we're not using like 1.1, 1.2, I just went ahead and said, all right, we're starting with the second term. So from the second term on, it's positive. And that's like ultimately positive, that's fine. Okay. And then for the decreasing part, my foot's falling asleep. For the decreasing part, foot's falling asleep, foot's falling asleep, foot's falling asleep. Oof. All right, so f prime of x is equal to low d high minus high d low all over low, which simplifies down to 1 minus ln of x over x squared. And again, you can do that derivative on your own if you want to make sure, but I'm setting that equal to 0. Where that's equal to 0 or undefined is at 0 and e. Okay, like, because if I plug e on top, I get ln of 1, which makes it 0. And so if I test some points into that, I'm going to get positive and negative. So e is like 2 point something or another. Okay, so past the point 2, starting at n equals 3, it's going to be ultimately decreasing. Okay, so that's okay. So it's a little bit of a stretch because at n equals 1, n equals 2, it's going to be increasing, but from that point on, the sequence is decreasing. So ultimately decreasing. Okay. So we showed all 3 of those criteria. We're good to go. We can go through the motions of doing the integral test. Okay. So let's see how it looks. So I'm gonna say that we're doing the integral. I'm gonna go ahead and say the limit as r is approaching infinity. Okay. Of 1 to r of ln of x over x dx. Okay. So in order to integrate that, actually we can do u sub. We can say u is equal to ln of x and du is equal to 1 over x dx. All right, substitute that bad boy in, and we're left with just the integral of u. Okay, and I guess I can write that out. The limit r is approaching infinity of the integral of u du. And something I didn't do last example, I want to do this example, is we will do u-bounds. So instead of saying like 1 and r, I'll say the ln of 1 and the ln of r. So I'll say the ln, oops. Okay, come on. I'll say the ln of r. And the ln of 1 is just 0. Okay. So if we integrate that, that's going to be 1 half. So I'm going to say the limit r approaches infinity of 1 half u squared from 0 to ln of r. I'm going to plug in ln of r. I'm going to plug in 0. Let's see what happens. So that's the limit. R approaches infinity of 1 half ln of r. That's absolute. That's actually not absolute value of r because we didn't integrate it. Sorry. So that's just ln of r squared minus the limit r approaches infinity of 1 half 0 squared. Okay. Now if we do each of those limits, okay, the limit of 1 half ln of r squared. Well, remember ln of r as that approaches infinity is just going to be infinite. So that's actually going to be infinity. And then 1 half 0 squared, that limit is just going to be 0. So because we have that infinite part, that means therefore the f of x is divergent, and therefore the series is divergent. And again, if you want to write that out, you would say that, since f of x is continuous, positive, decreasing, and divergent, therefore the series is also divergent. Okay. So yeah. So that's integral test. Okay, I thought that was pretty cool. Integral test is not too bad, not too crazy, I don't think. Um, and it's very procedural again, just like all these other tests. It's just learning when to do it, but just showing these things that I just showed, the continuous, positive, decreasing, doing the integral test. That's why I kind of started off with this one usually, is because I don't think it's the hardest thing in the world. It's more review than anything because we've done integral test. This is where it gets a little spicy. So let's see how it looks um, as I go over here. Aha! Okay. So normally this was when I would introduce the idea of what a remainder is and all that stuff. So we can still kind of discuss this because we're going to talk about our first error bound. So the series converges. Yay! Now what? Okay. Well, sometimes we can actually find the infinite sum, but a lot of times we can't. Okay. So we need to find an approximation to the sum S of the series, and any partial sum that we find, so just a piece of it, is just an approximation of the sum, right? So we talked about how to find out how good such an approximation is. We are going to do that by estimating the size of the remainder. Okay, that was our R of n that we talked about. So the remainder R of n is the error made when S of n, sum of the first n terms, is used as an approximation of the total. Okay, so that's like saying S minus, so this is my infinite sum, minus the partial sum. That difference right there is going to be what's left over. That's my remainder. That's another way of saying error. What's the error in my approximation? Well, it's just whatever's left over. Okay. Now we learned this with the which test have we already done this with? We did this with the alternating series test. Okay. Alternating series test said that the remainder, all right, was less than or equal to the next term in the series. Okay, that's for alternating series. So this was alternating series. Okay, but for integral tests, okay, if you're doing the integral test, there is a different way to approximate the um, the sum or the remainder. Okay, and that is this slide right here. I think alternating series, I think it was easier to show with that visual that I did, but with integral test, I think it's a little bit hard to show this, and I'm going to try my best. It says, suppose that you have some function that we represented as a sequence, okay, so that's part of the integral test. We showed that it was continuous, positive, and decreasing for all of x greater than n. So that's just saying, hey, it's convergent. Woohoo, okay? Now, getting to the piece that matters. Then, if we consider the remainder to be this, the difference between the infinite sum and the partial sum, which we've always talked about it that way, then this is how we estimate the remainder for integral test. What this is saying is that the remainder, all right, the remainder is going to be between n plus 1 to infinity of f of x, that area, that integral, and n to infinity f of x, that integral. So the error is going to be between the area underneath the curve of those two integrals. Okay. Now, as far as actually doing the math with this, it's super like easy because it's just integrals and y'all can do the integrals just fine. And as long as you know what n is, you can set these up no problem because this is just n plus 1 and this is just n. So the math and the setup is super easy as long as you can memorize this. Okay, but I would like to try to explain where it's coming from. So that's kind of my goal in this next little piece here. Okay, let's use an example. Let's say I have these criteria that it's positive or it's continuous, positive, decreasing for the function. Okay, and let's say I'm going to do like I'm going to talk about the remainder after 5 terms. So that's saying taking the infinite sum and subtracting s sub 5. And again, this is just an example. Okay. Well, let's draw that out. Okay. Let's draw out what S sub 5 looks like. Okay. So this is kind of basically what we're looking at here. Okay. So I'm gonna say A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 6, A sub 7, A sub 8. Okay. Now, wouldn't you agree? Okay, let's say that this is what the sequence looks like. Let's say the sequence starts off right here. Okay, then it's gonna go like here, then it's gonna go here, 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 and here. Now, wouldn't you agree that if that sequence was represented as f of x, that it would be a continuous motion through those points? It would be continuous, positive, and decreasing. Okay, so that's what the series is going to have to look like for us to be able to do the integral test. Okay. Now, let's say that I want to figure out what this fifth sum is. It's like taking the value of a sub 1 plus the value of a sub 2 plus the value of a sub 3. Now, in terms of a sub 1 is this value right here, okay? And because this is length 1 between a sub 1 and a sub 2, then wouldn't you agree that this right here, this rectangle, okay, is just going to represent the value of a sub 1, because it's whatever the height is times 1 is just still a sub 1, okay? So that's a sub 1 plus this would be a sub 2. I'm going to use a different color to talk about these points. Oops, that's not a point. Okay. And then the value of a sub 3 would be from is like the same as this right here. This is a 4 right here, and this is a 5 right here. Okay. So if I were to do my partial sum, it's the value of all of those right there. Okay. Now, if I'm doing the integral test, that means I'm going to have some function f of x. And this function f of x is a continuous function that goes through my points, right? It's not the sequence anymore, it's a continuous function. So what I'm saying is that the remainder, okay, now wouldn't you agree that the remainder is just going to be these values here added up onto infinity? Okay, it's going to be the remaining pieces. The remainder is equal to all of these pieces added up. What the remainder inequality here says is that if I were to take, say, in this particular example, r of 5, all right, that remainder is going to be between the integral of 6 to infinity of f of x and 5 to infinity of f of x, okay, based off of this rule of thumb up here. So it's saying that if I were to take the integral from starting at 5 to infinity, if I were to take this area right here, or take the area from, say, a 6 to infinity, I'm saying that my remainder value is somewhere between those two areas, which it may be hard to tell, but it kind of makes sense. Okay, the summation of the rest of the terms, okay, which is the remainder, is going to be greater than this grayer area, but it's actually going to be less than this green area. So it's somewhere in between these two integrals. Okay, and that's what I'm saying. So again, the remainder is these red blocks here. It's the remaining terms added up. And I'm saying that remainder is somewhere between the gray area and the green area. Okay. That's my best explanation I can do with that. But as far as like doing the math is concerned, as long as you know what n is, the setup is super easy. So let's do a couple examples of that, and then we'll call it a day. Okay. Cool. It says estimate the difference in your. I skipped one. There we go. Find the sixth partial sum of the summation n equals 1 to infinity. Well, that's super simple. Okay, if I want to do the sixth partial sum, that's s sub 6. That is the summation of n equals 1 to 6. Okay, n equals 1 to 6 of 1 over n squared. That's not bad at all. Okay, which you can do that by hand if you want. You could do 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. I mean, that's all. I mean, I'll write it out if you really want me to. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, blah, 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 blah. Okay, or you can just type this into your calculator. Either way, what it ends up is a big fraction, but as a decimal, it's 1.49. I'm gonna write out the whole thing. 1.4913888889. Okay. That's what I'm getting for the partial sum. Now this is an approximation of my infinite sum with 6 terms. Okay, so that's all we did so far. We just found an approximation. Okay. Now, we're going to estimate the difference between my answer in part A and the exact value of S, or the exact value of the sum for that series. Okay, that literally is asking me for, so if I'm saying the difference between your answers, so I'm saying the difference between S infinity and S6. That's another way of saying my remainder. I want to know what my remainder is, what my error is. Okay. Well, I know that, I'm going to try to set this up as best I can. I know, we'll do it right here, that my remainder, okay, with the 6 terms, I know that difference is going to be greater than or equal to the integral, okay, from n plus 1 to infinity, or 7 to infinity of f of x, or 1 over x squared. Okay, and less than or equal to the integral from n, which is 6, to infinity of 1 over x squared. Okay, that's just what the formula says. So again, I told you it's easy to set up if you just memorize the formula. I just wanted you to kind of conceptualize why that is from that diagram drawn before, and if you don't, not the biggest deal, as long as you can set it up. Okay. So now, if you notice, we have 2 integrals. We have 2 bounds here. All we have to do is just figure out the values of each of those bounds, and then I have my answer. So we're going to go through and do the integrals of each of these pieces. Okay. So let's see what we got here. I'm gonna try to set this up in like the least amount of steps possible for us. Yeah, okay. I'll go ahead and say the limit as r is approaching infinity of, of the integral 7 to r 1 over x squared less than or equal to r6 less than or equal to the limit as r is approaching infinity from the integral of 6 to r 1 over x squared. Okay. Now integrating each of those, we got the limit r is approaching infinity. The integration of that is negative 1 over x, actually. So it's going to be negative 1 over x from 7 to r, less than or equal to r6, less than or equal to. the limit r approaches infinity, the integration of that is, again, negative 1 over x, but we're going from 6 to r. Okay. So I'm going to have to set up. Oh, no. Yay, there we go. All right, so I'm going to set up each piece like we've been doing. I'm going to say the limit as r is approaching infinity of negative 1 over r minus the limit as r is approaching infinity of negative 1 over 7. Okay. Less than or equal to r6, less than or equal to the limit r is approaching infinity of negative 1 over r again, minus the limit as r is approaching infinity of negative 1 over 6. Okay. And we're going to evaluate each of those limits. Now the cool thing is the ones that actually have r in it are both rationals that are going to go to 0 and go to 0. So I got 0 minus, and the limit of negative 1 over 7 is just negative 1 over 7, less than or equal to r6, less than or equal to, and then that's 0 minus negative 1/6. So simplifying that, that's saying that my remainder of, after using 6 terms, is going to be somewhere between 1/7 and 1/6. Pretty cool. So crap, what's 1/6? Same thing as 1/6 is like 0.16, I think. Wait, right? 1/6. Yeah, so if you want to see this decimal wise, this is like 1.6666 repeating. And over here, 1/7 is like 0.142857, blah, blah, blah. So I'm saying my remainder is somewhere between, and I don't know why I said 1.6, that's 0.16, sorry. So my remainder, I'm only off by like a tenth or something like that, a tenth or 0.2, something close to that. My sum is pretty close to the actual sum. So anyway, there is your answer. That is estimating the difference between your answer in part A and the value of s. We are estimating the difference is between 1/7 and 1/6. My error, this is my error, is between an error of 1/7 or 1/6 off from the actual sum. Not bad, huh? So keeping that in mind, part C says, okay, well now, oh no. What? No, can y'all see this? That's not cool. No. Oh no. Okay. I really hope that that was weird. I was about to be very upset. Oh, what? Oh, come on. It didn't get the rest of that problem we just did. Well, it could have been worse, I guess. Okay. Well, we got the answer there. I'll go back and finish writing that out at the end of the video, but this is where we left off at. Jeez Louise. Okay. That was weird. So now it wants us to estimate the sum using the results from part A and part B. So here's what we're saying. I'm saying, okay, so if I want to estimate S, well, I know that S minus S sub 6, I know that that's going to be between 1/7 and 1/6 of the actual value. I know that remainder is going to be between 1/7 and 1/6. Okay, so if I know that's the case, then I'm going to plug in some values and solve for a bounds for s. I'm going to say s minus, and remember s sub 6 from part A was 1.491388889. I know that that's between 1/7 and 1/6. So if I want to know what my possible estimation for s is I'm going to add this value to both sides. I'm going to add 1.491388889. I'm going to add it over here. 1.491388889. Okay? And whenever I do that, I get S is between, all right, 1/7 plus that value, I got 1.6342 dot dot dot. And over here I got 1.6580 dot 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 dot. Okay. So my actual sum is somewhere between 1.6342 and 1.6580. I know it's probably going to end up being 1.6 something. So I got a pretty good estimation of what my sum is. Okay. And there you go. One more example, and this one's pretty easy. It says find the value of n. Okay, so I need to figure out now what the value of n is so that the partial sum s sub n is within 0.00001 of the actual sum for the series. So if I can use my integral test here, my integral bounds thingy here, I'm saying that I want it to be set up this way. I want my remainder. I want to figure out what my remainder is within terms. Okay. Or actually, I guess the better way of saying that, let's say this right here. Let's say instead of r sub n, we'll say s minus s sub n. Okay, which is r sub n. I want that difference to be off by no more than this decimal right here. So I want this to be like negative 0.00001 and positive 0.00001. I want that remainder to be off by that much. Okay. So how can I ensure that happens? Okay, so I'm trying to figure out what my remainder is to where I'm off or I'm within this bounds here. So I'm within this bound. So like the integral from like n plus 1 to infinity of f of x and the integral n plus, or just n to infinity of f of x. All right, I want this inequality to equal these values. I want to figure out what my n value has to be within those n values. So I'm just going to solve for that. All right, if I want my remainder to be this value or this value, I'm going to set my remainder equal to that, 0.00001. I want my remainder to be equal to that, and I want to solve for the n value that makes that happen. Okay, and that's it. I could have also set the left side equal to that, but I'd rather have n to infinity instead of dealing with a negative value 1 and dealing with n plus 1 in my interval. So if I can solve for this, okay, I'll have found my answer. So I'm going to do it this way. I'm going to say, well, I'm going to go ahead and just for sake of space, I'm going to go ahead and say f of x is the same thing as 1 over x to the 4th. Okay. And we're going to go ahead and set that up. So we're going to say 0.00001 is equal to the limit as, see, r is approaching infinity, okay, of the integral into r of x to the negative 4th dx. Okay, I'm going to integrate it. And the integration of that's what? Negative 1 over 3x cubed, right? So that's going to be the limit r approaches infinity of negative 1 over 3x cubed. Yes. And we are going to evaluate that from n to r. Okay. So I'm going to plug r in, I'm going to plug n in, I'm going to go through the whole motions again. So boom, 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 boom is equal to. All right, I'm going to do the limit r approaches infinity, okay, of negative 1 over 3 times r cubed minus the limit as r, oops, it's going to erase, r approaches infinity, okay, of negative 1 over 3n cubed. Okay. All right, now if I'm solving out each of these limits, I'm talking about the limit as r is approaching infinity. So that means that this bad boy is just going to go to 0. So I got 0 minus this limit. Since it's all in terms of r, this limit's just going to be whatever this quantity is. So minus a negative is going to make that positive 1 over 3n cubed, and that's equal to 0.00001. And now I'm just going to solve for n. Let's see if, well, I can say that it's like 0.00001 equals 1 over 3n cubed. If I do a little bit of math here, 3n cubed is actually equal to 1 divided by that number, which is actually 10, or actually 100,000. I can divide by 3 and take the cube root. And that's approximately 32.1829, blah, 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 blah. And because n is actually got to be like an integer, I can't have that decimal. So if I round it down to 32, that's not going to give me quite a large enough value to be like within my bounds. Okay. So I'm going to round it up to the next term, and that's going to be n equals 33. Okay. Yeah. All right. So there you have it. The remainder theorem, yay, all that good stuff. So hopefully that makes a little bit more sense now. Remainders and such like that. You don't need to know anything from these lessons as far as the AP exam goes. I just thought it was a good thing to know. So hopefully if you get bored, you can watch it. And hey, I kept it under an hour today, so 58 minutes. Doing pretty good. And I hope everybody's doing well, and I will talk to you all soon. Hello. Hello. Goodbye. Whew, I'm tired. Let's see, where's that stop button at? Should I go? Should I wait till it's an hour exactly? You dang straight I'm gonna wait till it's an hour exactly. I got a minute and a half left. So it's just gonna satisfy my OCD. But if it's a minute, if it's an hour, 1 second, I'm gonna lose my mind. So I'm gonna make sure I'm ready to click it as soon as it's ready to go. Okay. So I got a minute 20 seconds left. So what am I gonna do with that time? What am I gonna do with that time? Draw a smiley face. I hope people watch this video. I'm gonna be really upset because I tried really hard on it. And I only got 2 more lessons that are like officially done with calculus. I mean, technically we've already learned everything that's on the AP exam. I don't know. This quarantine thing's killing me. Not literally, but you know what I'm saying. I'm bored. Smiley face with some arrows. Can I draw right here? No, I can't. I can draw right here. Another smiley face. All right, 30 more seconds. And then I'll be at exactly an hour. What's Lasso do? What up? Just selects everything. That's pretty cool. Oh god, okay, 20 seconds. 20 seconds and I'll be at exactly an hour. That's pretty cool. Oh crap, 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 crap. Okay, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.